Hello, my name is Herson Esquivel-Vargas, and on behalf of my co-authors Marco Caselli, Geert Laanstra, and Andreas, I will present our paper titled Putting Attacks in Context, a Building Automation Testbed for Impact Assessment from the Victim's Perspective. To introduce the topic, let me start with the concept of building automation and control systems. Due to COVID-19, in the past few months, we have experienced what a predominantly indoor life looks like. To ease our stay indoors, a number of services such as heating, ventilation, and air conditioning are integrated into what we know as building automation and control systems. While some people might argue that these services are comfort-oriented, truth is that for different organizations with different requirements, such building services are actually enablers that allow businesses to execute the tasks that they are supposed to execute. You can think, for example, of an airport boarding gate, which is typically a closed room. Without proper mechanical ventilation in such locations, an airport can simply not operate. In this presentation, we talk about our experience in the construction of a BACS cybersecurity testbed and why we think that the organization requirements on the BACS must be an integral part of the testbed. Why a BACS cybersecurity testbed? Well, during the past 3 years, I've done research in BACS security, and I've benefited enormously from the traffic I collect from the BACS of the University of Twente. However, the access I have in this network is read-only, and when you work in cybersecurity, as I do, of course, you would like to have greater access than that. You would like to introduce your own packets, you would like to test some attacks, and unfortunately, this is not possible in real infrastructures. Now, by cybersecurity testbed, we mean a small-scale experimentation platform where we can perform all our research without any kind of constraints. There are different reasons to have such a platform, but of course, as I already said, cybersecurity testbeds are mostly about executing attacks in a safe way, but there are also a number of derived benefits from such a platform. For example, you can replicate attacks to achieve a better understanding of them, you can assess the performance of security solutions you might come up with, and you can also easily share the data without any kind of privacy or security concerns, like those you would have sharing data of real infrastructures. Why is the victim's perspective relevant here? Well, the task of BACS is mostly to control physical variables, which typically have a set point, although there is some tolerance on the fluctuations that it can take. In the plot here, you can see that we have a controlled physical variable, which can fluctuate in this wide region in the middle, and this is considered completely normal. However, there is this gray area at the top and the bottom of this plot. And the problem is that once the physical variable crosses those thresholds, we can say that the business that is being supported by this building service has some sort of affectance here. Now, coming back to the original question of why is the victim's perspective relevant, well, that's because the boundaries for each variable are different per victim, namely the organization that is being targeted. To illustrate this further, as a concrete example, this attack on the heating system of 2 residential buildings in Finland a few years ago caused the temperature to drop below the recommended values for residential buildings, which is between 20 to 24 degrees Celsius during winter. If these were not residential buildings, but perhaps unoccupied spaces, such as a data center, for example, then the recommended temperature values would be different. And this is exactly what we mean by the relevance of the victim's perspective. Now, in this paper, we argued that the testbed and the scenario should come together to achieve basically 3 things. First of all, a deeper understanding of the consequences of attacks. Then, in case of defensive tools are being demonstrated using the testbed, it is clearer where and when to use them. And perhaps one of the most important reasons to embed the scenario on top of the testbed is that, hypothetical attacks become concrete threats. So it's no longer about a buffer overflow or malformed packets that you're sending to a BACS infrastructure. It's now about physically hurting people or sabotaging organizations. We developed our testbed in 3 stages. First, define the requirements, then we moved on to the design phase, and finally we built it. We implemented our design. Let me start with the testbed requirements. The first requirement is that our testbeds must be capable of modeling different scenarios. Now, our goal was not to build a testbed that models a single use case, as it is typically done for industrial control system testbeds. Our challenge was to build a testbed that can model different scenarios using hardware and software commonly used in real BACS. Now, it is very difficult to emulate different scenarios in a realistic way, but for the purpose of our testbed, it suffices to configure the building services according to the requirements of the different business processes and business process locations. As you can see in this table, we have a list of business processes, like surgeries, teaching, and server hosting, along with some of the locations where those business processes take place, like operating rooms, lecture halls, and data centers. Now, for each of those locations, we have certain environmental conditions that are defined in different regulations or standards that state, for example, that in the operating room, the illumination should be in the range between 500 600 lux. Also in the operating room, the ventilation should keep the CO2 levels below 770 parts per million, and the temperature should range between 20 to 24 degrees. And similarly for the other locations. Now, this abstract modeling of scenarios by simply reconfiguring the building services according to the needs of the business process location makes it easy to add more scenarios if needed. The second requirement, and perhaps the most important one, is that we want to be able to execute attacks in our testbed. Now, there are many kinds of cyber attacks on building automation and control systems, ranging from attacks inherited from the IT domain, like botnet zombies or spam delivery, to the use of BACS devices as a pivot point to enter the enterprise network. Now, we are not looking at those kind of attacks. We focus on attacks where the adversary is trying to manipulate, disable, or damage physical control processes. This is a definition of attack taken from a Mitres attack framework. You can see the link below, and if you haven't heard about Mitres attack framework, I would highly recommend to take a look at it. So basically, in summary, our requirement here is that we want to be able to execute inter-process control attacks in our testbed. Our third requirement is we want to highlight the importance of having scenarios as an integral part of a testbed, and so we want to show how identical attacks on different scenarios yield completely different impacts. So this is the particular use case that we're giving to the capabilities of our testbed here. Although there are different kinds of impact, as I've mentioned in previous slides, our goal is to focus on the targeted organization, namely the hospital, airport, residential building, or many others, and therefore we use business continuity impact metrics as defined in ISO 27031. In this paper, we use two different approaches to estimate impact, one purely based on expert assessments, and one more robust approach that we developed in the past, namely the background methodology. And well, for time reasons, I will here discuss only the expert-based approach, but you can see much more details about the second approach either in this paper or in the original publication, where you can see the link below. Our design comprises all the necessary components to fulfill our list of requirements. As I mentioned before, we are building up abstract scenarios out of the building service requirements of business process locations. From the business process location, we take its environmental conditions and we use them to configure the building services accordingly. The building services that we consider in our design are ventilation, temperature control, which comprises both heating and cooling, and illumination. The next thing we had to design was the physical testbed itself, where we could be able to execute the kind of attacks that we are interested in, namely the inter-process control attacks. We designed our testbed using the 3D modeling software FreeCAD, and the goal of these designs is to make sure that there is enough space to fit all the components and wires that we need. For the sake of modularity, we decided to split our testbed in two components, which can be seen here in this slide. On the left-hand side is the model of a mechanical room where we have a heater and a cooler, which represent what in a real building would be a cooler and a chiller. And on the right-hand side, you can see a 3D model of a building room of our testbed, which will basically emulate the different business process locations, such as the lecture hall or the operating room or the data center. Now, let me start with the description of the building room. In the front panel, you can see an LCD on top, which will display the current configuration of the testbed, namely if this is currently configured as a hospital operating room or a lecture hall or any other scenario. There is a hole where we can insert a thermostat, which would be the main controller of our testbed. Also, in the bottom plate, you can see different power supplies because, well, of course, we have to provide power to different components in the testbed. And there is also an Arduino, which controls the LCD display in front and regulates the power to the high-power LEDs in the back on both sides of the router that you can see green in the back. Also in the back, we have a power socket inlet, two RJ45 connectors, one RJ11, and one DB9 connector. On the right-hand side of the testbed, we can see here a fan, which is, of course, the main actuator of the ventilation service. And on the left-hand side, there is basically a hole where we can physically connect a pipe that will connect the building room, namely this room we're seeing now, with the mechanical room on the other side. Now, the mechanical room is basically, you can see in the front panel, a hole that pairs up with the hole that you saw in the building room. There is also an RJ45 here because the electrical signals are sent using a UTP cable. And here you can see a power supply as well, a solid-state relay, heater, a cooler. And basically, because the cooler works with cold water cooling down the air, we have this hole here to make it easy to pour water into the cooler. In the back plate, we have a power socket inlet as well, and as an air intake, we use the logo of our university. With this design, we have a set of building services that will allow us to execute the inter-process control attacks that we want to execute. The design that we developed materializes with the implementation that I'll describe now. The BACS protocol that we're using is BACnet, one of the most popular building automation protocols. It's an ISO standard, and it's precisely because of its popularity that it's commonly scrutinized in cybersecurity research. As you can see in the diagram, we have a simple star topology IP network where we have this core switch in the middle and connected to it a number of different components. Starting on the top right side, we see two operator workstations, number 1 and 2, where we assume the second one is compromised by the attacker. On the bottom right, we have an historian, which you can think of basically as a database where we keep track of the different physical variables over time. And also connected to the core switch, we have in the middle the BACnet router, which basically behaves as a translator between IP communications and MSTP communications, which are used by the thermostat in the bottom at the middle. Now, the thermostat is connected to the different actuators using electrical signals, and these actuators are basically the heater, the cooler, the lights, and the fan. And since those actuators do not have a BACnet address on their own, they cannot be attacked directly. So the goal of the attacker would be to affect those actuators by means of the thermostat. And in addition to that, connected to the BACnet router, we have a modem that will allow us to connect our infrastructure to the public switch telephone network. And this is, of course, with the goal of having an attack surface as broader as possible so that the attacker can execute in many different ways the inter-process control attacks that we are interested in. Now, I don't want to spend much time in the implementation details, but I just want to show you here some pictures of the development process of our testbed. And I want to remind you that the 3D models, the bills of materials, and the network traffic, and many other resources regarding our testbed are available at this address that you can see at the bottom of this slide. To highlight the importance of the addition of context to our testbed, we performed the empirical analysis of different BACS attacks. As you might remember from the requirements section, we want to compare the different impacts that a fixed attack has over a series of different scenarios. In this section, we fixed the attacks that we will execute, namely attacks targeting the illumination, ventilation, and temperature building services, and we also fixed the scenarios under consideration, namely the operating room, the lecture hall, and data center, scenarios that we have been discussing throughout this presentation. As I already mentioned, there are different ways to compute a business continuity impact of cyber attacks, but the one that I'm discussing here is the expert-based approach, in which, using technical criteria, an expert judges which of the attacks has lower or higher impact based on the requirements of the overarching business process. While most people would agree that in an operating room all building services are very important, I hope you agree with me in that an attack on the illumination service has a very high impact relative to the others due to the immediacy of its effect. On the contrary to ventilation and temperature attacks, in which you at least have some reaction time before the variables cross a dangerous threshold. Similarly, an expert can use technical criteria to decide that for a lecture hall, for example, the illumination is medium impact, the ventilation is high impact due to the high concentration of people in a closed environment, and that the temperature is medium impact as well. Finally, for the data center as well, I hope you agree with me in that an attack on the temperature control service is more impactful than an attack on the illumination and ventilation services. These assessments are, of course, always relative to the location and the other building services in consideration. We executed different attacks in which we assume an attacker that's inside the BACS network and can therefore manipulate all the BACS controllers available. In our testbed, the thermostat is the main controller in charge of the heating, cooling, and illumination building services, and it's precisely with the illumination attack that we started our experiments. What you can see here in the diagrams is that all experiments start in the same way, namely the first roughly 40 samples. We start with a dark room, which means that the illumination is off. After this period, we enable the building service, namely we turn on the lights, and we keep it that way for a period of roughly 40 samples as well for all three scenarios. And what you can notice in this period is that for the operating room, we keep the illumination in the range between 500 and 600 lux. For the lecture hall, we keep the illumination in the range between 300 and 500 lux. And for the data center, we keep it between 50 and 100 lux, which is what we typically need in a data center. Now, you can also see this red vertical line, which means that we launch the attack. In this case, that means that we turn off the lights. And this basically causes that the physical variable, namely illumination, drops back to the initial values that we had. Now, as I mentioned before, the assessment, according to the expert, is that for the operating room, this attack is very high impact. For the lecture hall, this is medium impact. And for the data center, this is very low impact. And although this is exactly the same attack. Now, the second experiment we did is the ventilation attack. We executed the ventilation attack, and it's important to remind you here that by ventilation we mean exclusively the control of CO2. And in all the experiment, we first allow the system to behave as it should normally should, namely we keep the variable within the boundaries, and we trigger the fan when the CO2 level crosses a high threshold in this case. Now, you can see in the operating room and the lecture hall that, after a while, we have this red vertical line, which means that we launch the attack. And after that point, the physical variable, namely the CO2 levels, increase. And you can also see that after a while, the physical variable drops. And that's basically because the source of CO2 that we're using depletes. So you can see that it goes down for a while here. Now, it is important to highlight here that for the data center, we did not execute any experiment because we couldn't find any requirements on CO2 for these spaces because basically servers do not produce CO2 in place. So the third and last experiments that we executed is the temperature attack. And in this case, just as in the others, we first leave the system behave as it normally should, namely keeping the variable within the valid ranges. Once the variable crosses a threshold, the system will react and will bring down the variable, or will bring back the variable back to the normal values. And after a while, we'll launch our attack, namely that we disable the temperature control system. And what we can see here is that the physical variable, in this case temperature, goes well above the valid range. As you can see here as well, for the temperature case, for the operating room, we consider this medium impact, for the lecture hall, medium impact, and for the data center, high impact, despite the fact that in all cases it's exactly the same attack. Let me conclude with a few takeaway messages and lessons learned from our work. The most important takeaway message of this presentation is that a testbed must come along with one or more scenarios because this will give you a better perspective for the research that the testbed will uphold in the future. In this particular paper, we have shown the usefulness of those scenarios on top of a BACS testbed to perform simple impact assessments, but other research can benefit from those scenarios as well. For example, to develop robust intrusion detection systems that consider the context as part of the detection mechanism, to perform realistic attack and defense training for red and blue teams, and to provide illustrative attack demonstrations where you not only show the effect of the attack on the physical components of the testbed, but you also consider some of the scenarios where you envision this attack might take place. Just to stress this further, the hardware in our testbed is essentially similar to the hardware in existing testbeds. What's different is the addition of scenarios, which has been overlooked in previous BACS security testbeds. One limitation of our testbed is that we have a few building services, but this is of course because there is a trade-off between the fidelity of the emulated business processes and the complexity of the testbed that you're willing to have. And finally, one note on the particular use case that we gave to our testbed, namely the computation of business continuity impact scores. And it is precisely that those scores are linked to physical variables and not to the specific cyber attacks. And this distinction is important because this decouples the overall goal of the attacker with the specific attack procedure employed. For instance, the impact of shutting down the air conditioning in a data center is the same regardless of how the attacker does it. A final remark here, I just want to remind you that the 3D models, bill of materials, network captures, and many more resources are available at this address that you can see in the bottom. With these final remarks, I would like to thank you for your attention, and although there is no traditional Q&A session, I'll be happy to take any questions by email. Thank you.